All right, so what is the definition of free fall? What does it mean? When we talk about free fall, what is that? Falling what? Other influences. So what's the only thing that is influencing the object? Gravity. Just gravity. Okay? So when an object is in free fall, that is your definition. So you got to remember that. You might want to jot that down. Means that the object is free from other influences and then gravity. So gravity is the only thing that is causing that object to go down, to go to the ground, and that is the force of gravity. So it does not depend on the object's mass. It does not depend on what the object is. It does not depend on anything other than gravity. Okay? So that is important to remember because it's not always what we see. So if you look there, free-falling objects are always accelerating, so you need to know that. Free-falling objects are always accelerating. For an object tossed in the air, the acceleration is the same on the way up and on the way down, regardless of whether it's thrown upward, downward, or just dropped. Okay, so if I take this ball and I throw it up, okay, the acceleration going up is the same as the acceleration coming down. Okay, whether I do this, and drop it, or whether I just drop it, or whether I throw it up in the air, it's the same. Okay, the acceleration going up is the same as that going down.
Wait, what?
Uh-huh.
So what if I chunk the ball up?
You chunk it up.
Yeah, as hard as I can.
Okay.
Wouldn't the
acceleration? We'll probably get to that one. But we talk about if you chunk it, is it necessarily in free fall? When is it in free fall? So when we're talking about free fall, we're talking about the only influences on it being gravity. Okay? So keep those things in mind. Then we'll start doing some problems and looking at different aspects of it. Oops. So acceleration is produced by gravity at the Earth's surface, and it's denoted with a G. Okay, so before, all of our acceleration equations have had an A in it, right? A for acceleration. Well, when this particular chapter, or this particular part of this chapter, our acceleration, if an object is in free fall, is represented with a G. Okay, G for gravity. And it is a constant number. As I said, it's the same, whether we throw it up, whether it's coming down. Acceleration due to gravity is the same number. Memorize that number. I will not give you that number. In a problem, all they'll say is the object is in free fall. You are expected to know that that means acceleration due to gravity is 9.8 meters per second squared.
Wait, so I can remember every single one of them?
There's only one.
Oh, it changed in Hong Kong.
Not enough for us to worry about. Right? Because if you look at the table, it is 9.79 as opposed to 9.8. That's not enough for us to worry about. Okay? That's just showing you that it is due to gravity. And the force of gravity is not the same everywhere in the universe. if we go to the top of Mount Everest, the force of gravity is a lot less than it is at sea level, than it is on literally at sea level. If you went to New Orleans, which is actually below sea level, and you compare the gravity there to the gravity on the top of Mount Everest, it's going to be different. Now, the difference is going to be small, as you see, teeny tiny, but it's still different. If you went to the moon, of course, it would be dramatically different than here on Earth. Okay? So that's just showing you it is due solely to gravity, and gravity does change slightly depending on where you are. Yes.
So, what planet has like a super high gravity? Jupiter.
I think it is Jupiter.
So if we
Maybe Saturn. Is Saturn more than Jupiter?
I would assume Jupiter.
I think Jupiter's the most.
So if
Yeah, because it depends on the object's mass. So Jupiter, if Jupiter's one of the bigger planets mass-wise, then it's going to have a stronger force of gravity.
So if we lived there, would we have like tree trunk legs?
Yes, and you would probably be very, very short and very stocky, you know, as opposed to somewhere else where you might not need as much muscle or whatever, if you could do that. Okay, so the 5 constant acceleration equations of motion can be used to determine the position and velocity of a free-falling object by substituting g for a. So all of those equations that you learned at the beginning of chapter 3, they're the same equation, but instead of a, we put g. So instead of telling you what the acceleration is in the problem, they're going to let you have to remember and assume, oh, it's always 9.8, okay? So in your problems, they won't tell you acceleration is whatever. They will say the object is in free fall, or they will tell you the situation and you're going to have to discern that the object is in free fall, and so the acceleration you're going to use is 9.8. What about the sign? Got to remember that sign. What does the sign of acceleration indicate? The direction you're going in. Whether you're going with gravity or going against gravity. Okay? So in this particular case, if you're going with gravity, that would be positive. If you're going against gravity, that would be negative. Okay? All right. The velocity of an object in free fall increases linearly with time. Okay, so, and that should make sense. It's just a fancy way of saying, if I drop this ball, every second that it's in the air, it's going 9.8 meters per second faster, which means right before it hits the ground, it's going to be going its fastest speed.
Wait, I thought we just said it was always accelerating. Doesn't mean acceleration is changing. Just kidding.
Right, exactly. Good. Don't second guess yourself. You were right. Okay. The distance increases with time squared. Okay. So if you're talking about how far is it going to wind up falling, that's going to be it increases with time squared. So you're going to use that formula. Like I said, all those formulas that you learned at the beginning that are on page 80. What is that? 88. Yeah. All of those formulas are going to be exactly the same, but wherever there's an A, there's a G. So the final position is equal to your initial position plus your initial velocity plus 1/2 times squared, AT squared. So if we didn't chunk it, just say we dropped it, what's our initial velocity? 0, right? If I just drop this, it doesn't have an initial velocity because I dropped it. I didn't push it, okay? So its initial velocity is equal to 0, which means, let's write that formula up here. XF xi vit plus 1/2 gt squared. G just means a, acceleration. So that's going to fall out to 0. Its initial position, of course, is going to be 0. So its final position is just dependent on gravity, how long it stays in the air. Okay. So same equation. You don't have to memorize anything new. Same equation. It's just we're replacing A with G. And then, of course, if we're dropping it from a building, those other variables are going to fall out to 0. And so your equation is going to kind of collapse down. And it's just dependent on the gravity and how long it stays in the air. Yes?
So why is your T 0? Because the start is.
Because 0 times anything is 0, right?
Yes, ma'am. I'm so sorry.
No, you're fine. That's exactly right. That's what you need to be.
That's very good.
That's what you need to be recognizing and answering. So that's fine. All right. Okay, so here is a graph of an object in free fall. Okay, it is not a straight line, obviously, and it is an upside down parabola. So let's look at what is happening at each stage of the object in free fall. Let's see if this is anywhere in your book. Yes, this is on page 101. So position and velocity change differently in free fall. So look at page 101, or you can jot this down. I would jot this down in my notes. The position time graph of free fall motion reveals some symmetry. It's a parabola. So that means it's going up to a peak, and then it's coming down the same exact way on the other side. So here's our initial velocity. So if it has an initial velocity of 29.4 meters per second, what does that mean that we did with this ball, Cappy? Well, this ball has an initial velocity of 29.4 meters per second. What does that mean? What did I do? I threw it up, okay? Threw it up in the air. It rose to a certain point, and while it's going up in the air, it is accelerating 9.8 meters per second squared. Okay, so at 1 second, it is going, now notice, what's it doing? What's happening to the velocity as we go up? It's slowing down. Why is it slowing down? No, it's going against gravity. Exactly. The velocity is going in one direction. Acceleration due to gravity is going in the other. So that's slowing it down. Okay? Eventually, it's going to keep slowing down, so eventually it has no velocity at the top of its peak.
But it still has acceleration.
What is happening to, when it reaches that 0 velocity, what's going to happen to it eventually? What happens to all things eventually? They come back down, correct? Why is it coming back down? Gravity is pulling it back down. Okay? So now it's coming down. So its acceleration is 9.8 meters per second down, but its velocity is slowing down. So look at the velocity. It's the same magnitude, but look at that sign. Negative. Why is it negative? Not that it's traveling backwards or anything. What's it doing? It's going in the opposite direction from where it started. So went up, goes up, okay, then comes back down. Right? So it's the same velocity on both ends, because the only thing that it's due to is acceleration due to gravity. So that negative sign just means the direction in which it's traveling. Okay? So that's why you'll notice that on the other side it's negative 19.6 meters per second. And it hits the ground, or right the split second before it hits the ground, its velocity is negative 29.4 meters per second. That means it's going to end up with the same magnitude of velocity that it started with, but its direction is different. Instead of going up, it's coming down, and it's right about to hit the ground. Okay?
How does it have the same? Oh, wait, okay. I'm trying to connect velocity and acceleration. Never mind.
Okay. All right, think about it. Yeah, try and process it, think about it, and then come back to it in a minute. Because I believe, yeah. So we got all the time in the world to sit here and process that because that's the end of my slide presentation. The only other thing we're going to do now is we're going to work on some sample problems. So let's start with the sample problem on 312 because there's a follow-up. Number 51 and 52 are follow-ups on that. So let's go through the guided example on page 312. Let's see if I have this in my PowerPoint somewhere.
We can share.
312. This may be additional. No, I'm sorry. It's page 99, example 312. Do the cannonball. There we go. I found it on the screen. Here we go. Okay. So, boy steps off the end of a 3-foot high diving board and drops into the water below. How much time does it take him to reach the water? And what was the boy's speed on entering the water? So, if we draw a sketch of what's going on. So here's our diving board. We know it's 3 meters above the surface of the water, so that's about 9 feet. If you're trying to picture that in your brain. And so he's jumping off. We want to know how much time it takes him to reach the water and how fast he's going. So there's our sketch. His initial position, of course, would be the edge of the diving board, which would be 0. What's the only thing that's bringing him down to the surface of the water? Gravity. So is he an object in free fall? Yes. Okay. So his initial position is 0. His acceleration is that of gravity, which is 9.8 meters per second squared. Okay. His final position is 3 feet. His initial velocity is 0. He's not running and jumping off. He's doing a cannonball. So you're just standing there and he just jumps. So we're going to use this equation. XF equals XI plus VI plus 1/2 AT squared. So XI is going to be 0. The VI times T is going to be 0. 1/2 times 9.8 meters per second squared times time squared. The only problem is, of course, I do not know what the time is. Right? So that's what I've got to find out. Oh, actually, that's not true. I'm sorry. I don't have 2 unknowns there. What did I mess up on, guys? I have the final position. $3 meters. Okay? So, how am I going to solve that for t squared? Or for t? Because I don't want t squared, I want t. So what am I going to do? Take 9.8 times 0.5 is 4.9. Okay, what now? By 4.9. So what is that? Divide it out. Use a calculator. Punch in the buttons.
Then you got a square root.
You do. So just tell me what it's equal, and then we'll do the square root. One at a time, one step at a time. It's not a large number. It's a small number. Less than 1. Let's see, what would we round it to? Looks like 2 decimal places. Yeah, 2 decimal places. 0.61. So it'd be like 2 significant figures. That's meters squared per second squared. So how do I get t? I take the square root of that. And what's the square root of that?
0.78.
Yep. So it takes him 0.78 seconds to hit the water. Okay, any questions on that? So with that, you gotta have your basic equations in your brain, and then you have to remember his initial velocity is 0, his initial position is 0. So the only thing, if he's in free fall, the only thing that his position depends on is the time he's in the air and acceleration due to gravity. Okay, so now how are we going to find the second question? How are we going to find question B? We have to find the final, what was his speed? How are we going to do that?
BF squared.
We could. What would be another way we could go?
Oh, duh, the easy one. BF plus A, or whatever.
Yeah. Like I said, we could do the other one, but this one's a little bit easier. VI plus AT. So what's his initial velocity? 0, so that's going to fall out. So his final velocity is just equal to acceleration due to gravity times how long he was in the air. So what is that? 7.6 meters per second squared. Or meters per second, sorry. Okay. Because the second squared is in the bottom, and that seconds is in the numerator. Okay? Any questions on that one? Oops. They kept it to 3. They did 3 significant figures or 3 decimal places. Again, that's fine. So if we did that in everyday units, because we don't go around talking about meters per second very much, so it's kind of hard to judge of what that actually is. He would be entering the water at 17.2 miles per hour. That's pretty fast. So if you ever go to Point Mallard and you get on that super high dive, which is way more than 9 feet, how high is that?
9 feet. That's gotta be like 50 feet.
Yeah, I know, that's what I'm saying. It's way higher than that. 9 feet would be the ceiling. The ceiling is probably actually 10 to 12, so around there. So that thing it's got to be at least 50 feet. So think about how fast you're going when you hit the water.
You're dead.
No, if you do it right, you're not. If you're doing a cannonball, you're okay. Or if you know how to dive, you're okay. But that's also why the water on that end of the pool is how deep? Yeah, it's like 15 feet because if it wasn't, that's how people break their necks. When you have a shallow end of the pool and they have that little sign all over the place that says no diving, that's why there's no diving, because you're going to hit that water at a certain speed and you're going to keep going, and if you wind up hitting that concrete, you're going to break your neck.
Listen, you angle it right. That is true. That is true.
You would have to angle it and change the shape of your body in mid-flight so that you come back up, and that doesn't always happen.
It is doable. Very doable. I do
But
it
it's
all the time.
also like playing Russian roulette.
Do it all the time.
And is it worth it?
I don't think so.
No. So when they tell you don't dive into the shallow end of a pool, that's why they say don't dive in the shallow end of the pool. Okay? Or even, if you're talking about, and this happened to a cousin-in-law, he just dove in the ocean and he thought it was deeper than it was, and he dove in head first and hit a sandbar.
Ow.
Now, thankfully, it didn't paralyze him, but it did stun him. So for a little while, he couldn't move because it, shocked those nerves in that spinal cord, and for about 24 hours or so, he couldn't move. So if that had been a pool, or if he had hit maybe just slightly differently, he could have been paralyzed. So when you're diving, you want to make sure that there's nothing else around and that you're not going to wind up hitting something and damaging that spinal cord. So, okay, enough of my little motherly. Don't dive into the deep end of the pool. Okay, so let's look at 51. 51 is a follow-up to that problem. So I think I need my screen here. So repeat part B of the guided example 312 using the equation. Okay, so Reese, they're going to use your method and see if we get the same thing. So VF squared equals VI squared plus 2A delta X. So this, again, is going to fall out to 0. So the only thing it's going to depend on is the distance that it traveled and acceleration due to gravity, which is 9.8 meters per second squared, times the change in distance was 3 meters. Okay, so look at your units and see, are my units going to wind up working out? And they are, because I'm going to wind up with meters squared over seconds squared. And then I'm going to take the square root of that, and what do I have? Meters per second. Okay, so 2 times 9.8, 2 times 9.8, times 3, 58.8, and then we're going to take the square root of that, and it is 7.67, exactly the same as what we got before. So it's just two different ways of working the same problem. Okay. All right, so let's look at 52. Another follow-up. What is the speed of the boy in the guided example 3.12 on entering the water if he steps off a 10-foot high diving board? So now, or 10 meters. 10 meters, not 10 foot. That's a big difference. So now we're going to change this. What are we going to change about this? Yeah, we're going to change x from 3 to 10. Or I could go back and use that other equation if I wanted to. But this would actually be easier because I wouldn't have to go back and figure out anything else. I wouldn't have to refigure time. So, oops, there should be a decimal right there. So 2 times 9.8 times 10 square root. What does it come out to be? If I multiply that and take the square root, what do I get?
14.
14. Okay. So just for the fun of it, what is that in miles per hour? Because I'm curious now. Let's see. How many meters are in a mile? I think it's 1609 meters in 1 mile. Yeah, that's why I'm just basing that off of track. A 1 mile is about 1,600 meter race. I think it's 1,600. And then 3,600 seconds in 1 hour. So 14 times 3,600 divided by 1,609. 31 miles an hour. 31 miles an hour.
Would it be the same if we had left it as meters squared per second squared? You know, and taken the square root?
That would, what now? Say that again.
Did we finish the problem originally?
We did. That's how we got 14.
Okay.
Yeah.
I'm looking at it. Okay.
Okay, so what I'm gonna do, I'm gonna leave y'all with some time to, well, we'll do 1 or 2. We can either go back over 3.3, or I can give you time to work on practice problems. The lesson checks for 3.3.
Hold on, let's see what this is.
Remember, 3.3 is the position versus time graphs. And after doing research on that problem number, 45 and 49, the only way to solve that equation is to use the quadratic equation. There's no other shortcut. You got to use quadratic.
So can we do that? Because I wouldn't remember how.
I would have it on the test. I would have the quadratic formula on the test. What is it? B plus or minus the square root of, is it B squared
B squared.
minus 4AC
Yeah.
divided by
2A.
2A?
This one.
So I would have that formula on the test. And the way you would know that you have to have the quadratic formula to solve it is because when you simplified your equation down, all you got was t and t squared, and you can't solve for 2 variables. Can't solve for 2 unknowns. So the only way to solve that is to put it in the quadratic. So if you ever get that situation where you have a t and a t squared, or an x and an x squared, you're going to have to. So I think with that one we had like 1,000 equals some number plus, I'm making up numbers here, 2t minus 3t squared. Okay, so let's say that was your equation. And you can't solve for t and t squared at the same time without anything else. So you would put this whole thing equal to 0. So that would bring that as negative, what is that, 997. And you look at what the a and the b and the c are your coefficients in this equation. So your a is going to be this coefficient, b is going to be the one with the t, and your c is the constant. C starts with constant, same letter. But so the coefficient in front of the square term is your a, coefficient in front of the regular variable is your b, and the number is your c. So that's how you know which one is which. But so if you ever get an equation that you get to this point and you can't simplify it anymore, and you've got a square and the same variable there, and you can't do anything else to it, you can't factor it out, you can't find a perfect, what is that? perfect square, binomial, whatever, can't do anything else to it, then your only option is quadratic formula. So to get it in that form, you get all the stuff on one side, you set it equal to 0, and then your term in front of the square is a, your coefficient in front of the single term is b, and your number is c. So. And of course, when you do all quadratics, when you do them, you get two solutions. That's the point of the quadratic. You get two solutions. Only one solution is going to make logical sense. So if we're solving for t, which is time, and you get a negative answer and a positive answer, obviously the negative choice is not reasonable, correct? Because we cannot have negative time. So you would choose the positive answer as your answer. Okay? So to me, that was the really hard one of section 3.3 is having to do that stupid quadratic. But it is what it is.
So what's the answer?
What's the answer to what?
45.
45? The answer to 45 is 24 seconds. The answer to 49, which I think did the same thing. A is 6.3 seconds, B is 22 meters, and C is 10 meters per second.
B was what?
22 meters,
What was it?
10 meters per second.
Is there any way we could do, like a portion of 49? Because I don't know.
Yeah. Yeah.
Did I ever know? I'm
Okay.
Giant.
A bicyclist is finishing her repair of a flat tire when a friend rides by with a constant speed 3.5 meters per second. 2 seconds later, the bicyclist hops on her bike and accelerates at 2.4 meters per second squared till she catches up with her friend. How much time after the friend rides by does it take for the bicyclist with the flat tire to catch up? Okay. So it's the same concept as the example in 310, where the police car is catching up to the speeder. But did they give you the All right, so if they're catching up to each other, their final position is going to be equal. So that's where we're going to set these two equations equal to each other. So it's going to be xi vit plus at squared equals xi for the second person, flat tire person.
Is it half 18 squared?
Yes, it is.
Okay, sorry.
No, missed it. Do what? Yes. Okay, so So their initial positions are both going to be 0. The first bicyclist, the one that passes by, has an initial velocity of 3.5. Make sure you take fast. Meters per second. They didn't take fast. Going at constant speed. So if it's going at constant speed, we're going to have an acceleration. No. So, okay, so this is the bicyclist that flies by. So has no acceleration because she's just going along at 3.5 meters per second and she never stops. She just keeps going. Okay. Our flat tire person, again, position is going to be 0. Their initial velocity then would be 0 because they have stopped. Their acceleration, it says, we are told in the problem, is 2.4 meters per second squared times t squared. Okay, so let's see what we can do with this. We may not have to use the quadratic. We might be able to. So this term right here is all going to be 0, right? Because 0 times anything is 0. So that leaves me with 3.5 meters per second times time. This term is going to be 0. Oh no, we're going to have to use it. 1/2 times 2.4 is 1.2 meters per second squared times t squared. Am I solving for the right thing? How much time? Okay.
If you divide by t on the left side, wouldn't it give you just t on the right side?
Let's try it and see. So meters, seconds. So 3.5 divided by 1.2. Right. That's not gonna. We missed something. That comes out to be 2.9. It's supposed to be 6.3.
Wait a minute.
So we missed something there. Something's not right.
What number is this?
49. Oh, look what I did. Good grief. That 2 seconds is going to factor in somewhere. Hang on. So let's think about that. 2 seconds later, the bicyclist hops on her bike and accelerates. seconds later. So how are we gonna account for the fact that it's 2 seconds later? She's on down the road 2 seconds before the other girl gets on her bike and starts to head out.
Use her speed and find the distance, and then that can be her initial.
Well, that's right. I mean, it makes logical sense. For the girl who keeps riding with a constant velocity, we know her speed. Let's put in 2 seconds here and find out what her. Say that again.
I meant like go off to the side, not use that formula, and
Yeah.
just do 3.5 meters per second, and then find if you're going for 2 seconds, how many meters you travel, and put that in for your initial position.
For her initial position, rather than having that be 0. Okay? So we would use, this is the equation you're talking about?
Honestly, half the time I don't know how to use equations, I just think about it.
But that's what you mean, right?
I get it this way.
Find. No. That's not what you were talking about.
No.
That's not it. The VF equals VI plus, well, no, we wouldn't use VF.
Yeah, you would just use like the basic speed equation, so for velocity, so it's like distance over time.
Okay.
If you're going 3.5 meters per second, then you've gone 3.5 times 2.
Exactly. Right.
So 7, right?
So that is 7
Yes.
meters.
So plug that in for.
So we're going to plug that in up here. All right, so yeah, yes. What did I read? You know what you're doing. Now this is going to give us, we got to use the quadratic formula, but, you know. So we're just going to get all of this on one side. So 1.2 t squared minus 3.5 t
I want to look like a pin strap.
minus 7. And then use quadratic formula. I'll finish this out and put the solution on. Yeah, I think you're going to have to. Because the other way we did it, it didn't work. Didn't give us the right answer. Because we weren't accounting for those 2 seconds. If they had started at the same time, then that would be different. But they didn't. So.